Now, what if we have not only is z a function of two variables, but what if x and y themselves are also functions of two variables? So we can extend this, really, I guess, indefinitely. Okay. Yeah, there's many different scenarios here that we could tap into here. All right, so we've got z is a function of x and y. And then also, x is a function of two variables. Let's say it's a function of s and t. And then y is also a function of s and t. So we've got two variables here, but then the x and the y themselves are also functions of two variables. It's a lot going on. Okay, well, what actually makes sense then in this case is to think about the partial of z with respect to the s. That would make sense, right? Because, yeah, z is a function of x and y, but x is a function of s and t, and y is a function of s and t. And so essentially, z is a function of s and t as well, right? And so, anyway, now it's going to make sense to talk about the partial of z with respect to s, and also the partial of z with respect to t. Same idea, basically same idea. So we do, since it's first of all a function of x, we do the partial of z with respect to x. Then x itself is a function of s and t, so since I'm doing the partial with respect to s, I would need to multiply this part by the partial of x with respect to s. So now I am doing a partial derivative here, because x has both s and t variables in it. What would I add to that? Do the same thing, but with the y, yeah. So do the partial of z with respect to y times the partial of y with respect to s. And that would give me the partial of z with respect to s. And then the partial of z with respect to t, same thing, except these would be partials with respect to t, right? So it would be partial of z with respect to x times the partial of x with respect to t, plus the partial of z with respect to y times the partial of y with respect to t. And it's not exactly what's going on here, but you can kind of see why this works a little bit, because if you think of these as fractions, look what happens here. Your partial of x's eliminate, and so you're left with partial of z with respect to s, right? Partial y is partial of z with respect to s. Yeah, okay, so makes sense that way too. All right, so let's do one of those. Okay. It's really the same as before. Okay, so z equals x squared plus 2y, x equals s over t, y equals s squared plus ln of t. So let's find the partial of z with respect to s. Looks like a 2 right there, doesn't it? Okay, so the partial of z with respect to s, I would do the partial of partial of z with respect to x. Multiply that by the partial of x with respect to s. and then rotate that to the z. All right, so the partial of z with respect to x, we have just 2x. Partial of x with respect to s, well, let's change that to s t to the negative 1. Yeah, so that'd just be t to the negative 1 or 1 over t. Plus then the partial of z with respect to y, just be 2. The x is constant. And then the partial of y with respect to s, just be 2s. And that would just be 0 because it's s partial derivative with respect to s. So that's just 2x over t plus 4s. Okay? All right, then we would have the partial of z with respect to t. We could do that also. Couldn't we? All right, so that would be the partial of z with respect to x times the partial of x with respect to t. And then do the same thing for the y's, partial of z with respect to y, times the partial of x, the y, partial of t. Okay, so what would that be? Partial of z with respect to x, we already did that, it's 2x. Partial of x with respect to t, though, that would be this one. So it would be negative s t to the negative 2. All right? The s is constant, so it stays in there. All right, then partial of z with respect to y, we already did that, that's just 2. But the partial of y with respect to t, well, that's constant, so that's 0. Be 1 over t. And so that is negative, let's write it negative 2xs over t squared plus 2 over t. Yeah, you could do combining or factoring or different ways you could write that form out. All right, not too bad, not too bad. Now, we get more and more complicated. The basic structure stays the same. It's just keeping all the parts separate, or getting all the parts in there, I guess we might say. And so one idea they also mention is the idea of this tree diagram. So let me mention that for the previous two we've done. All right, so if we've got z, let's go back to the first version. Z equals f of x, y. X is also a function of t. And y is a function of t. Okay. So the tree diagram, what it is you start here with z, and it kind of branches off because it's a function of x and y. So it branches off, or we've got x and y, and those combine to make the z. Now we're not saying that that's how we form it, but it's some function of x and y. Well, x is also a function of t, and so it essentially, we take a t, and that gives us whatever function via whatever function. So anyway, we just kind of structure it like this. They call it a tree diagram because you're kind of just branching things together. So this is a pretty simple version, but anyway, here's how this works, or how it helps us with this chain rule. Okay, so I want to talk about here dz dt. And so from the tree diagram, what we've got is dz dt then is the product of all the derivatives along this path from t to z. So you do all the products of the derivatives from t to z, and then you add those together. It's the sum of all the products of t to z, of all the derivatives from t to z. So essentially here, along this path, you've got a, let's see, that would be dx dt, and then the partial here of z with respect to x, kind of getting from here to here, you see. And then this would be the partial of z with respect to y, and this would be dy dt here. And so you see these paths here. So the path from t to z, you've got dx dt, partial of z with respect to x. So you product that together, so it's the same thing. Plus then partial of z with respect to y, dy dt. So it's the product of these paths added together. Okay? Now if we have z equals f of xy, and then x is a function of s and t like we had, g of s and t. Y is also a function of s and t, h of st, let's call it. Then again, we've got z, got x and y combining to make it. But then, what happens off of x? We've got two branches, right? We've got s and t here, and then y's got s and t branched off of it. And so, yeah, so if I do the partial of z with respect to x, s, well, I've got this path, which is partial of x with respect to, z with respect to x. And then this is the partial of x with respect to s. Let's do it in the order that we did it before. So you have the partial of z with respect to x times the partial of x with respect to s, plus then you have this other path from s to z, right? So you got to do the partial of z with respect to y, and then the partial of y with respect to s. And so that kind of shows you all the, let's do it in the same order. So it's partial z with respect to y, partial y with respect to s. I don't know, in that case, if it's any easier to do it that way. However, they'll use a whole lot of different possibilities for this. So let me do another one, and let's use the tree diagram to get our partial derivatives here. Okay, so let's see. Use a tree diagram. To write out the chain rule for this scenario. All right, so we got u equals a function of x, y, and z. Okay. U is a function of x, y, and z. And then x is a function of s, t, and v. And y is a function of s, t, and v. And then z is a function of s, t, and v. Okay? What do we got for a chain rule there? Okay, so here it is. We've got u at the top, and then x, y, let's kind of spread these out, x, y, and z off of it, And then for x, well, it comes out of s, t, and v, right? Let's put those out as far. Right? And then y, s, t, v, and then z, s, t, v as well. So, what derivatives make sense here? The partial of s with respect, or partial of u with respect to s would be one of the derivatives for the chain rule here. So what would it be? Well, we've got three paths from s to u, don't we? And so we do the partial of u with respect to x times then the derivative here would be the partial of x with respect to x, s. And then the other path from u to s would be u through y. So the partial of u with respect to y, partial y with respect to s. And then last but not least, u to s through z would be partial of u with respect to z, partial of z with respect to s. So it's really not, you're just extending it more further and further out a little bit. And then you do the same for the others, right? From u to t, so it'd be the partial of u with respect to t. So through x, you'd have the partial of u with respect to x, partial of x with respect to t. Yeah, it's pretty much the same as above, isn't it? Except we're doing t's instead of s's, right? The only thing is, that works because all three of these are the same, s, t, and v. If that changes, that wouldn't quite work quite as nicely as that. Oops. And then the third one, do the same for the partial of u with respect to v, right? So the partial of u with respect to x, partial of x with respect to v. Okay? Partial of u with respect to y, partial of y with respect to v, and then the partial of u with respect to z times the partial of z with respect to v. Be the three chain rule equations for it. Okay. All right. Let me do this one. Kind of an example here. Let's say we've got P equals the square root of u squared plus w squared plus v squared. It's v squared plus w squared. And u equals x e to the y. What did I say? U equals x e to the y. V equals y e to the x. And w equals e to the xy. Okay, let's just find one out. Let's find partial of p with respect to y if x equals 0, y equals 2. So what do we have here? We've got a path from P through U, V, and W. That reminds me, too, of something else I forgot to mention. A path from P through U, V, and W to from, and those are from X and Y, right? Those are functions of X and Y. So this is kind of the structure we've got. The other thing I was going to mention, I forgot to mention on the other one, is we've kind of got, like we said, P is essentially functions of X and Y. So this level here we would consider our independent variables, right? Like we've talked about in the past. So those are independent variables. And then P is kind of dependent on those, right? Essentially what we're saying there. But we have this middle level here now, and so those are termed intermediate variables. If you hear that term thrown out or something like that, I don't know if it's mentioned in the homework or not, but just in case. So yeah, if you have this middle level, they're usually termed as intermediate variables. These are independent. Got that mostly on there. So, all right. So anyway, we're looking for the partial of P with respect to Y, and so we've got what, 3 paths from Y to P. So we need to do the partial of P. So we come P, U to Y, so or P from U and Y. So that would be the partial of P with respect to U times the partial of U with respect to Y. Plus then, we can come to Y from P through V, so that would be the partial of P with respect to V times the partial of V with respect to Y. And then through W, we'd have the partial of P with respect to W, partial of W with respect to Y. So what does that give us? Well, the partial of P with respect to U, I don't know why some of them sometimes look at the 2's there. Okay, what would that be? Well, you got a nice, that's U squared plus V squared plus W squared to the 1/2, don't you? So you got 1/2 U squared, V squared, W squared to the -1/2 times 2U, the derivative of the inside, would be 2U there. So then we would have the partial of U with respect to Y, so that would be what? X e to the Y? Just doing the partial with respect to Y there, so the X is constant, so the derivative of e to the Y is e to the Y. So, all right, then we've got partial of P with respect to V. Well, it'd be the same thing as partial with respect to U, except now we're doing V with respect to V, and so it would be the same thing, all right, 1/2 U squared, V squared, W squared, so -1/2 times 2V, though. And then the partial of V with respect to Y, what would that be? So the partial of that with respect to Y, just be e to the X, yeah. And then last but not least, our partial of P with respect to W. All right, so that'd be 1/2 the U squared plus V squared plus W squared to the -1/2 times the derivative of the inside with respect to W, just be 2W. Then the partial of W with respect to Y would be, move this over just a little bit. partial of that with respect to y. We're just doing the derivative. It's e to the y. So the derivative of e to the y is e to the y, right? Leave a constant with it.
Okay, so you just
yeah. So the v, we're doing the derivative of y. So the e to the x is constant. So the derivative of the y is just 1.
Oh, yeah, because of the
Okay. Yeah. Yeah, we're doing the derivative with respect to y. That's okay. No problem. But yeah, there's a lot to keep track with. That's the thing about these. All right, e to the xy, derivative of it. Well, a couple ways you could do it. You know, it's e to the xy. And then the derivative, if we do a chain rules, then do the derivative of the power, just be x, right? Times x. Okay, all right. I know I can cancel these 2's out all the way across. But I was interested in a particular value. X is 0, y is 2. If x is 0, y is 2, what is that going to mean? Well, that's going to mean u is 0, isn't it? V is 2 times e to the 0 is 1. And w would be e to the 0, so that would be 1, yeah. So that would make this, what, 0 squared plus 4 plus 1, so that would be 5 to the negative a half times u, which is 0. Oh, didn't even need that. Yeah, because all these are, yeah, those are all zeros. Okay, then this would be also 5 to the negative a half times v, which is 2, e to the x, which is 0, so that's 1, plus 5 to the negative a half times w, which is 1, e to the xy, should be 1. X is, okay, that's also 0, so that's gone, that's gone. So it's just that. 2 over the square root of 5. Okay. It didn't turn out to be that nasty after all. Okay. Okay. So yeah, you just get a lot of parts and pieces, so you got to really watch. Watch and keep track of everything. Got off my screen. Yeah, okay. All right.